Good morning, everyone. Quick show of hands. I know Jan Odegaard showed us this, but how many of y'all are from Houston? Good. Today's talk will hopefully not only tell you about how we predict or build predictive models of damage risk to your homes. I mean, your takeaway message also, because I'll show you lots of pictures, the risk profile of your own home in Houston. So even if you find what I say, uninteresting, you'll still have a takeaway message, which is, wasn't I smart in purchasing my home here, which is sort of not subject to all these risks. Okay, so today I'm going to talk about using big data and machine learning to build spatially fine-grained models of wind and flood damage risk. So in a way, I'm going to do a deep dive into one particular problem that I've been working on for some time with colleagues from the civil engineering department, Leonardo, who's right there, and two colleagues from political science. The reason is, at the end of the day, we engineers, we build predictive models, but who consumes them, right? People. So we also need to understand how we can actually move the needle on people's behavior. Because if all we do is sit in our closed rooms and make these amazing models, ultimately we want to influence people's behavior. So what particular behavior are we talking about? This is the map of our wonderful city. The arrow points to where we are right now. And this is taken from a map of the Office of Emergency Management here for Harris County. And these color-coded zones are really the places where you will need to evacuate. These are surge zones, and mandatory evacuation policies are in effect whenever a storm comes up, up Galveston Bay. So the yellow regions are evacuated with a Cat 1, green regions with Cat 2, and the orange regions for a Cat 3 storm. The interesting thing is the bulk of our population lives in the non-surge zones. That is, the areas that are white on this map, all right? So 4 million people, about 50,000 live in these areas. The rest of us are here. But when we hear news of a storm, all these red roads, by the way, are evacuation routes. What ends up happening is we do not provide any information about hurricane risk to all of these people. The implicit assumption is none of you are at risk, stay put, shelter in place. Okay, that's not what we saw with Hurricane Rita. We saw that a bit with Hurricane Ike. And Harvey, I think, came up a little too quickly for our taste. So there wasn't enough time to evacuate. The point is, we need to inform. So these people are also at risk, and we need models that can help us, at a fine-grained level, explain to people who live in all of these areas what their risk profile is with respect to rainfall flooding and with respect to wind risk. So the subtext of today's talk actually follows up on Rick's talk, which is what is the role of simulation models or models that are based on physics, and the role of data, and how we can play off of them to actually build better models than either approach can provide us. All right. So why is this an issue? We're all, in Houston at least, familiar with the problem of shadow evacuation. The people who are in the white zone are not people who shelter in place. There may be people in the surge zones who do not evacuate in spite of repeated warnings, but people in the white zone, will clog these exit pathways out of our city because, I live in Maryland, and if I get on these roads, really all of these roads get clogged because of people like me jumping on the highways trying to get out of town. This phenomenon is called shadow evacuation. These are people who are not at risk and decide to evacuate, making life really difficult for people who are actually in harm's way. Here's a little bit of shadow evacuation math. The Houston transportation network can handle about 750,000 commuters every day. But when you add up to 500,000 people in the coastal areas who need to evacuate through Houston, you've basically stressed our transportation system significantly. So it's very important to be able to build accurate models of risk so that we can tell people in the white zone who are truly at risk for wind damage or flooding, so only those people can, are able to or need to get out from here. So the new map from the Office of Emergency Management should, for every storm, color code all of these regions, giving us information about risks so we can make, as citizens, make informed choices about evacuation. So what is the state of the art for predicting wind risk? Wind risk is a particularly difficult problem, right? Because essentially, we're asking for every home, this is the level at which we'd like our models, is your home at risk for wind damage with the oncoming storm? So the two approaches currently available are one based on physics, and I will show you that in a moment. Build engineering models that estimate risk to a structure due to wind and rain, embodied in a program that FEMA uses in order to assess damage in advance of a storm. It also uses that to allocate resources, and the Office of Emergency Management uses this particular model to determine where to position its emergency resources. All right, so it's a widely used model, 20 years to develop. It's valid. Okay, so when a model like this is built, and a question to ask is, well, has it been validated? Yes, there have been small-scale validation studies done. There has never been a large data set collected after a storm to be able to evaluate the performance, the predictive performance of this model. The other approach, which I'm going to talk about today, is a data-driven approach where you learn models that predict risk based on observational data. All right. So here is the structure of the engineering model. I'm going to go into it in a little bit of detail so you understand the structure of this model. One of the most difficult things when you want to build a predictive model is to understand what are the aspects of the problem that actually predict wind risk. So think about a home in a wind field. What aspects of it really matter in terms of predicting whether that home is going to get damaged by wind? The structure of the model is a decision tree where you look at, is the home wood framed? Most homes in our area are wood framed. There are separate decision trees for buildings not built out of wood frames, but I'll show you the most common one. Then we look at whether it's a 1 or a 2-story home, the shape of the roof, whether it's hip or gable, the nailing patterns on the roof tiles for the roof, and then finally, whether the roof is actually strapped on to the structure, right, or whether it's nailed. Okay, and you're saying, wait, where's the deep learning? Didn't she promise me that? And now she's going through a litany of these factors. It's important that you look at them because the model that tells you right now, that tells FEMA whether you are at risk is really this model, right? So these factors are known because construction codes dictate this. And the tax appraisal district maintains information about the structure of your home, whether it's 1 or 2-story, et cetera. So at the bottom of this decision tree, once you've figured out, so my home is a 2-story home with a hip roof, I think with a 6D 12-inch, and it has hurricane straps. All right, so I would fall in here. So at each of these, there is a probabilistic model. On the x-axis is the peak gust wind speed in miles an hour, and on the y-axis, the probability of a particular damage state, minor, moderate, severe, and destruction. So if you want to predict what is the probability of moderate damage, you would look at the green curve. So this is how the model works. For every home, about a million homes in our area, it actually figures out which of those curves should apply, and then it averages that. So it gets a probability. And then it groups all, so every home will have a number attached to it between 0 and 1, which is the probability of it being damaged with an oncoming storm. The data is grouped or aggregated by census tract. And so for every census tract, we're going to get a picture of sort of the average probability of damage. Decisions are made on the basis of that. Of course, the question is, well, that's a nice model. I can explain it this quickly. How well does this model perform? So we got a unique opportunity in 2008 because Hurricane Ike came our way and caused a considerable amount of damage. And the Harris County Housing Authority commissioned a damage assessment of 800,000 homes, providing us a big data resource, first for assessing model performance, and then I'll show you for directly building a model for predicting wind risk from observational data alone. So how well does this model perform? Oh, I was supposed to animate that, but never mind. In August 2014, my students and I found a way. We used this data of 800,000 homes where damage assessments were made, and I'll share with you the results of that particular evaluation. Here is the wind risk model for Hurricane Ike, predicted by that model I spent a few minutes talking about. You can tell that the highest risk area is over here, and these are expected to suffer very small amounts of damage. This is what the data showed us. This is the observed data. To make it clear, let me show you a side-by-side comparison at the census tract level. So we're comparing apples and apples. This is aggregated to census tract. This is aggregated to census tract. Clearly, we have a problem. So what can we do? Well, we analyzed the error structures and found that the model actually under-predicted damage in all of these blue areas, over-predicted damage in these red areas, and was correct in 60% of the census tracts. If we reduce the spatial granularity and analyze the performance of the model at the 1 kilometer square block level, see, census tracts are kind of ragged shapes, and people don't often know what census tract they belong to. A 1 kilometer square level model is useful because it's at a human scale. We understand, okay, my home is in this little square. How does that do? So this is the prediction of the model using the same methodology that I showed you with the probability curves. And the errors look like this, where again, blue stands for under prediction and red stands for over prediction. Here, only 51% of these little squares are predicted correctly. So let's pause and think about what that means. That means, you know, I could have run a coin and colored these, and I would probably get something like this. If this doesn't disturb you, friends, I don't know what will. So why does this model perform so poorly? What is the problem? Well, we have 800,000 homes, right? So let's do some error analysis using machine learning. What are the characteristics of the census tracts and blocks where the model makes errors? So we're going to follow an approach like this. We're going to take this data, 800,000 rows, and whether that home was predicted correctly or not. And because remember, we're getting at a per home level a probability. And we're going to use this data to figure out whether we can separate homes that are correctly predicted by the model from those that are not. But what should what should these covariates be? How should we build such an explanation? All we know is the model predicts this home will be damaged with a probability 0.2. The empirical data says it was damaged. Now what do you do? So this is where physics starts to become important. Because how do you formulate the vocabulary for expressing performance of this model. What are the factors that might be important? After a lot of work, and by consulting with our friends, both from political science as well as from civil engineering, we came up with the following features to explain model performance. Terrain features, what is the land cover? Is there a tree within 100 meters? Is the home near a highway? Roughness length, which is a terrain parameter, indicating how treed an area might be. Building properties of various sorts. Construction code enforcement. Oddly enough, we found that we could explain a lot of house failures really by whether construction codes were enforced. Now, we couldn't have come up with that without the help of our political science friends. And hazard characteristics, because wind is the ultimate cause of damage. You know, when people talk about deep learning, they always say, well, feed this data into the network and miracles will happen. Well, feed what data? That's the point. If all you have is 800,000 homes, their addresses, and whether or not they were damaged as deemed by a civil engineering inspector, you don't have a lot to go on, right? You have to actually add additional information. That's what we're adding here. So the explanatory variables that I showed you, I just want to run through a couple of them. Notice that the homes that were damaged tend to be, are not very good. I mean, the building value is pretty low. They're old buildings, and they're of generally lower quality. So even at this level, you can begin to see that there's some logic to these. Here are more of those, but I'm not going to spend a lot of time on them. Here is the wind profile. But I just wanted to show you that this is the kind of additional data we had to feed into the model to be able to understand why the engineering models didn't perform that well. So we were able to build a random forest classifier that actually identified which of the things were correctly predicted and which were not. So to understand the model itself, it's one thing to build a model. A random forest model is not a deep model. I'll show you a deep model in a few minutes. But we wanted something that was readily interpretable, right? Because we wanted to modify the engineering model so it could do better. Well, better than the 51% that we saw. So the analysis involved building what is called a variable importance plot. And this actually tells you which are the aspects that actually contribute to correct or incorrect prediction. Notice that building value, age, quality, land value, whether or not the garage is detached, and whether or not, and when the home was incorporated into Harris County. These are factors that determine whether a home is correctly predicted. These are not factors that are taken into account in the engineering model. When you look at the block level performance, that is the 1 kilometer square level, notice that quality, building value, the same aspects come back again. Let me give you a quick view of sort of what we learned. The engineering model predicts a probability that a home will be damaged on the basis of these parameters: the frame, the floors, the roof shape, roof deck attachment, nailing pattern, garage type, terrain, and wind speed. We found that only these 4 were relevant. What this analysis revealed is there are a whole bunch of other parameters that were not taken into account and that are critically important for determining whether a home will be damaged or not. So you might say, gee, I mean, I could sit at my armchair right now and tell you these things are relevant. How come the engineers didn't take that into account? Well, fortunately, I'm the computer scientist here, so I will let my peers in civil engineering answer that. But I just want to say that this is a phenomenon I see again and again in many, many problems, not just in the world of civil engineering. So let's not beat up on our civil engineering colleagues. I work on problems in biomedicine, and definitely we see this kind of, blinding. So when you're building physics models, you really want to take a minimum set of parameters in order to explain the phenomenon. And that sort of need for minimality often makes you ignore factors that you think will be taken care of somewhere else. This is really the role of data. If we didn't have these 800,000 homes, we could not have produced this nice list of things that we absolutely need to take into account. The other aspect is detailed explanations of why these models were wrong. So all of these were mispredicted by the model because of ignoring the quality of the structure. So now we can go in and, with the models that we built, begin to understand both at a census tract level and even at the kilometer square block level, the different types of mistakes that were made throughout. So this gives us direct ways of fixing the engineering model. But that's not what we wanted to do. We said, why not build it directly from data? We now know we need more parameters and more complicated functional forms to estimate the damage probabilities. There were many more questions to be answered before we could start on the job of building a prediction model. At what level should you predict the risk? At the level of an individual home? At the level of a block directly? At the level of a tract? And how should you evaluate the model? Which kind of ties into what should the prediction target be. It's interesting that our engineering friends built models that predict at the level of an individual home and then aggregate up those probabilities to either kilometer square or to census tract level. Why do they do that? They do that because you can get a lot of detailed information at the home level that you can bring to bear on prediction, so you can build a pretty accurate model. Because if you were building models at the level of a kilometer square block, you would have to have a notion of an average house in the block. And so you're really smearing the probabilities on all the inputs. You don't want to do that. So here was the plan then. We'll use our data on 800,000 homes. We will use the explanatory variables that we built up for our error analysis and now try to predict directly whether a home is damaged or not. Gradient boosted trees were the best. We tried many things. And we evaluated accuracy at both the residence level as well as at the block level. Here's our performance of the model at the individual home level with the boosted decision tree. 80%. Hooray. Stop the presses. We will print this. At the kilometer square block level, we got an accuracy of 89%. Double hooray, right? Wow. So how should we evaluate these models at all? By the way, we followed the best practices of evaluating models in this. We did cross-validation. We did train test splits. So it's not like we are training and testing on the same data to give us these artificially inflated, so it seems, estimates. How do we really test the performance of these models? Ideally, heaven forbid, we get another storm, we get new data, and we test it out, right? We don't want that. So how should we test it? So here's what we did. We took our model and tried to predict it for storms that had appeared before, like Alicia, storms that we hope never occur, like Rita that bypassed us, a Cat 5 storm. And we basically discovered that the model had been overfitted to the Ike scenario. So even though the numbers are amazing, and it would probably pass muster in a machine learning conference, because we've certainly followed best practices, when you looked at the structure of the model, it was too close to the Ike. So this is always a danger with these models. So if someone comes around selling you a machine learning model, you have to have other ways of testing, but the model is not overfitted. And that means you have to be able to peer into the model and understand its structure. The models were hard to debug, and physics was not helpful, alas. So what do we do? We decided to actually start from raw data and really integrate all the data sources. So rather than have us manually craft features from the factors that we think are important for predicting wind damage, we'll start with wind data from NOAA, and this is at a, I think, 30-meter resolution, land cover data, 30-meter resolution, the damage data, this is labeled data on an individual home from Ike, HCAD data, which is from Harris County. This is what our tax appraisal district maintains information about every home. All kinds of properties are recorded. And finally, very detailed 50-centimeter resolution LiDAR data. So we said, well, with all of this very, very detailed data, without us telling the machine exactly what is relevant, so we're not building all the explanatory variables that I showed you before, are we able to, how well can we do at predicting at the home level? This was the question. Lots of challenges, because data is at varying spatial resolutions. This class imbalance, only 20% of the homes were damaged in, well, 20% of the homes were damaged. So that's high, but from the point of view of a machine learner, you'd like a 50-50 thing. And then have to learn relevant features and the decision function jointly. So that's the thing. This is ongoing work with an undergraduate student of mine. And this is the deep architecture for predicting wind risk. We use all of the information in a two-stage process. We start with the LiDAR image. So we put a home in the center of this LiDAR image, take a 200 by 200 meter tile. I'll talk about how we process that. Then we put the wind and all of the tax information, the HCAD information up here, land cover and all of that. So this is integrated in this pipeline, LiDAR image, a pre-trained VGG convolutional layer, and I'm running out of time, so I will tell you that this model is able to predict at 0.7 at the individual home level. This I actually believe. This I believe will scale to other storms because we are uncovering interesting aspects of the terrain, the values, etc. In fact, we can produce these saliency maps that tell you sort of what aspects of the terrain really correspond, are responsible for damage. So this map is built by essentially zeroing out a square in here and then seeing the impact, running the model on it. Essentially, we're told if these homes were eliminated, the risk to these homes is going to go much higher. So these are very interpretable. Our ongoing work right now is tuning these architectures, tuning the training protocols, and we will be publishing this in the next month. I think we've used, essentially we're inferring the physics from these learned distributions. So we are learning by visualizing the weights and the activations of these networks, these deep networks, we're able to finally understand what are the aspects of the terrain that contribute to a home being damaged or not. And that is the insight we want. If you're a developer, you want to build homes, you will know where to site them and what the impact of placing it next to a highway might be, or in a treed development, etc. In the 2 minutes I don't have, let me tell you about analyzing flooding. And this is highly relevant because we're all coming off of Harvey. I was personally affected, live in Ireland, and if I had trusted my models, I would not have bought my home there. But we are going to predict at the home level in Houston whether or not to flood. Our competition is a very detailed physical model. It basically models the soil structure, the land slope, all kinds of information to model water flow when, rain comes from the sky and when bayous jump their banks. This takes very long to run because if you want an accurate model, you put a very fine mesh over the entire Harris County, and it may take you several weeks before you come up with a risk model. I would like to use available data sources, rainfall 311 calls, which we make when you're at home and need rescue during a flood, floodplain designation, and digital elevation models. So I'm going to show you the 311 call density. So anytime you experience any kind of these events, you can call a service, and they record data. This is 2011 to 2015. Can you tell which areas in Houston get flooded a lot? Why should we not use this to actually make predictions rather than simulate the soil chemistry of Houston? We could actually do quite well, is what I want to say. And without that, 51% of homes not in designated floodplains experience more than one flood. So these are homes not on a designated floodplain, and this is a scatter plot of distance from a bayou to the number of times they got flooded. There's a poor house got flooded 14 times. And you will see that you could be 2 kilometers from a bayou and still experience more than one flood. So we're going to use this information. So here's the picture I want you to have in mind. 311 calls, floodplain designation, LiDAR, rainfall data. Take all this information and let's cluster these calls on the basis of rainfall, bayou distance, floodplain, and call frequency. If you do that, here's what you see. You get 3 distinct clusters in Houston. You're very close to a bayou, you're in the floodplain, and you have more than 2 floods on average. Well, that's the cluster I belong to, alas. Cluster B, you're far from the bayou, you're not in the floodplain, and you have more than 2 floods on average. Well, unexpected. And it's actually 54% of homes. The other is you're close to the bayou, you're in the floodplain, and you have just only 1 flood on average, 1.58. So let's look at this green cluster, which is cluster B. We are far from the bayou, you're not in the floodplain. So what we did there is we took all those homes, put a tile, a 200 by 200 meter tile from the LiDAR data, and actually analyzed them. We clustered the LiDAR signatures. We found 2 very interesting signatures. High density development and proximity to large tracts of land at low elevation. Do you see these homes? And this is all, when it's dark, it means it's lower. So this is a signature of homes in that category. The other is, I don't know if you can see the road here, it's a major intersection in these high density developments. There are other signatures, but I think we are now itemizing the types of patterns around the city that predispose you to these. I think these are much more interesting models. Finally, let me end with this slide. Data-driven analysis is a useful stand-in for physics-based models. When physics-based models are not accurate, data can help you understand what's wrong with them and improve them. But there are limits to data too, right? Because you will ultimately need to add additional information, not just damage data, to be able to build these models of risk. So I apologize for going over, and I will take a few questions.
I'm absolutely sure she could take question, but that means that we will not have a break before the next session. So.